Uh, Welcome back, everybody. It's my pleasure to introduce Professor Kaneenika Sinha from IISER Pune, and she will be talking on explicit construction of unbalanced Ramanujan bigraphs. Kaneenika, let's go.
Yeah. Good afternoon, everyone. Thank you, Purushottam. It's wishing Professor Balasubramanian a very happy 70th birthday. 5 years ago, we had two big celebrations to celebrate his 65th in two different cities in India. But this time it looks we have an even more massive celebration with so many people across so many continents and countries joining in. So today I want to talk about some recent joint work with Shantanu Prasad Bernwal and Mathukumali Vidyasagar. They are electrical engineers at IIT Hyderabad, and they had a very specific interest in the theory of Ramanujan graphs and bigraphs because of some very interesting applications that these types of graphs and bigraphs have in engineering. So I'd like to talk about this work. So we will go along at a leisurely pace. We'll first start with some basic aspects of graph theory, introduce definition of Ramanujan graphs and bigraphs, and try and understand why they are so important in number theory. And we will then move on to certain very nice and explicit constructions of what are called unbalanced Ramanujan graphs and try and understand the use of these bigraphs from the point of view of applications as well. So a graph consists of a vertex set V and an edge set E, which is contained in V cross V. So for any two vertices, Vi and Vj, we say if Vi comma Vj lies in the set E, we say that the vertices Vi and Vj are joined by an edge. And if Vi comma Vj lying in E also implies that Vj comma Vi lies in E, that is, if we don't worry about the orders, then the graph is said to be undirected. So we will be assuming that all the graphs in today's talk are actually undirected graphs. Okay, now these Vi and Vj are said to be the endpoints of an edge Vi comma Vj. And a loop is an edge with the same endpoints. We will further assume that the graphs in this talk are simple graphs, so they do not have any loops. Now, the degree of a vertex V refers to the number of vertices X such that X comma V lies in the edge set. And a graph is said to be a D-regular graph if every vertex in the graph has the same degree D. Now, a path in a graph is a sequence. So we are not just worried about edges now. We can have a sequence of edges moving across various vertices. So this is defined by the notion of a path. A path in a graph is a sequence of distinct vertices in the vertex set, except possibly V1 and Vk, such that Vi comma Vi plus 1 for each I lies in the edge set E. And if V1 is equal to Vk, then we say that this path is a cycle. And the length of a path is the number of edges in the path. Okay, now we have this notion of diameter of a graph. So as I mentioned before, henceforth, we consider finite, undirected, simple graphs. A graph is said to be connected if any two vertices in the vertex set can be joined by a path. And the distance between any two vertices, U and V, is the shortest length of a path joining them. There can be more than one path joining U and V. So the length of the shortest path is what is called the distance. And the diameter of a connected graph is the maximum distance between all pairs of vertices. Okay, so for example, let's take the most obvious example that comes, the most immediate example that comes to mind, namely the complete graph on n vertices. So this is a graph on n vertices such that there is an edge between any two vertices. and one can see immediately that this is an n-1 regular graph, and it has diameter 1. Now, a cycle C sub n on n vertices can also be interpreted as a 2 regular graph, and its diameter is the floor function of n over 2. Now, how does one judge the efficiency of a graph? So typically, graph provide us with a mathematical model for situations where you have networks. So situations where you have different nodes and you have connections between subsets of these nodes. And how do we judge the efficiency of a graph? Suppose you have a graph with a very large number of vertices, but very few connections between them, meaning you have big clusters of vertices which are not joined by edges from other clusters. So those graphs will not be very helpful from an application point of view. So the other extreme situation is that you have a large number of vertices, but you also have a very, very large number of edges, for example, in the complete graph. But there, the problem is that of use of too many resources to ensure connectivity across all nodes. So to judge how efficient how efficient a graph is, or what is the quality of a graph, one notion is to understand the diameter. So if you have a graph with relatively small diameter in comparison to the number of vertices, that would be a good graph from network point of view. So this takes us towards the topic of Ramanujan graphs in the following way. So there's a very famous 1989 theorem of Fan Chung, which provides a bound for the diameter of a connected d-regular graph in terms of a quantity called the spectral gap of the graph, which in turn depends on eigenvalues of the graph. So let's go over that notion. So suppose we label the vertices of a finite graph as v1, v2 up till v sub n. We can define what is called its adjacency matrix as an n by n matrix in which the ijth entry is 1 if vi comma vj lies in the edge set of the graph and it is 0 otherwise. Okay, so since X is an undirected graph, we immediately see that the adjacency matrix is symmetric and therefore it only has real eigenvalues. These eigenvalues are called the eigenvalues of the graph. Now, some eigenvalues can be deciphered immediately from the information given to us. For example, if X is a d-regular graph, then you can immediately see that your D, because the row sums of all the rows in A is D, one can see that D itself, which is the degree of regularity, is an eigenvalue of A, and this is usually referred to as the trivial eigenvalue. Moreover, by some more work, one can also show that for any eigenvalue of capital X, the absolute value of the eigenvalue is bounded above by D. So, in particular, we have the notion of a spectral radius, which is the maximum of the absolute values of all the eigenvalues of the graph. And in this case, we know that the spectral radius is bounded above by D. In fact, since D is an eigenvalue, the spectral radius is exactly equal to D if you have a d-regular graph. So now we label the eigenvalues of a d-regular graph as follows. So we refer to D as lambda 1 of X and the next one as lambda 2 of X. And so now lambda 2 of X can also be equal to D. In fact, one can talk about the multiplicity of the eigenvalue D, and that is equivalent to visualizing how many connected components your graph has. So keeping aside the trivial eigenvalue, so any eigenvalue whose absolute value is equal to D is called a trivial eigenvalue. And we define lambda of x to be the maximum size of the so-called non-trivial eigenvalues of the graph. So now how is all of this connected with the diameter? They are very, very closely connected. So if you have a connected d-regular graph on n vertices, let d of x denote the diameter of x. We have certain very nice theorems which relate the diameter to lambda of x, which is the size of the maximum size of the non-trivial eigenvalues of x. So these are different inequalities due to Alan Millman in 1985, Fan Chung in 1989, and Van Dam and Hamers in 1995. And you will observe from all these inequalities that to minimize the diameter, we need to minimize lambda of x. So in this connection, there's a very famous theorem of Allen and Bopana in 1986, which says the following. Suppose you take some number d, positive number d, and fix it, and you consider d-regular graphs on n vertices, then as n goes to infinity, then the limit infimum of lambda of x sub n is greater than or equal to 2 times square root of d minus 1. And in particular, a d-regular graph x is said to be a Ramanujan graph if lambda of x is less than or equal to 2 times square root of d minus 1. So this represents the optimal situation with respect to lambda of x derived from the Allen-Bopana bound. Okay, in other words, in a Ramanujan graph, all the non-trivial eigenvalues lie in the interval minus 2 times square root of d minus 1, comma 2 times square root of d minus 1. Okay, now we move to some very special graphs, namely bipartite graphs. So a graph is said to be bipartite if you can partition the vertex set of V into two sets, VR and V sub C, such that the vertices in each of the sets, VR and VC, among themselves are not connected to each other. So there is no edge between any two vertices in VR or any two vertices in VC. So if there is, so for any edge in this graph, the edge must join a vertex in VR to a vertex in VC. A bipartite graph is said to be balanced if VR and VC have the same cardinality and unbalanced otherwise. A bipartite graph, furthermore, is said to be dr-dc biregular. So when we were talking about d-regular graphs, we have to specify a degree. Here we specify, so we are talking about a larger class of graphs now. So we say that a bipartite graph is said to be dr-dc biregular if every vertex in VR has degree dr and every vertex in VC has degree d sub c. Now, obviously, this because if you count all the edges as either coming out from the vertex at VR or coming out from the vertex at VC, it immediately tells you that DC times the cardinality of V sub C is equal to dr times cardinality of VR. Okay, so for again, an immediate example is the complete type. Question? Any questions? Okay, so we have the complete bipartite graph K sub m comma n, in which you have two vertex sets with m and n vertices, and there is an edge between each vertex in VR and each vertex of V sub C. Okay, so now when we talk about bipartite graphs, especially unbalanced bipartite graphs, then instead of eigenvalues of the adjacency matrix, we can talk in terms of singular values of another matrix, which I'll now explain. So first of all, as I mentioned before, the multiplicity of the degree d as an eigenvalue of a d-regular graph equals the number of connected components of the graph. A connected d-regular graph is a bipartite graph if and only if minus d is also an eigenvalue of the graph. And something very special happens in bipartite graphs. The spectrum, namely the eigenvalues of the graph, turn out to be symmetric about the origin. So if lambda is an eigenvalue, then minus lambda will also be an eigenvalue of a bipartite graph. Okay. So now when we have a bipartite biregular graph with degrees dr and dc, then in the adjacency matrix, there will be large blocks which will just contain the entry 0. So the really relevant part of the adjacency matrix is what we call the biadjacency matrix, where the rows are labeled by the vertices of VR and the columns are labeled by the vertices of VC, and the entries 0 and 1 appear as per whether a certain vertex is connected to a vertex in the other set or not. But now, obviously, in many situations, capital B need not be a square matrix anymore. So that's why we can talk about singular values of these rectangular matrices B. So in particular, in a dr-dc biregular graph, square root of dr-dc is the largest singular value of the biadjacency matrix B. And in case you have not heard the definition of singular values, it simply refers to the square roots of the non-negative eigenvalues of B transpose of B. Okay. So the relation between eigenvalues of the adjacency matrix and the singular values of the biadjacency matrix can also be written out clearly. So the eigenvalues of A equal plus or minus sigma sub I, where there are L many sigma i's, L being the minimum of the cardinalities of VR and VC, and sigma 1, sigma 2 up till sigma L are the singular values of B. Okay, and there are also certain number of zeros which will show up. So zeros, a zero with a certain multiplicity will show up as an eigenvalue of A. We now denote analogously to the notion for eigenvalues of graphs. We can talk about bipartite, biregular graph, and we can talk about sigma of x, which we denote as the maximum of the absolute values of the biadjacency matrices, of the biadjacency matrix, which are not equal to the trivial, the so-called trivial singular value. Okay. And as an extension of Allen-Bopana theorem to this setting, suppose we take dr comma dc and we fix dr and dc, and we take a sequence of vertices, sequence of sizes of vertices nr and nc in such a way, of course, that dr nr has to be equal to dc times nc. So with this restriction, if your n sub r and n sub c tend to infinity, then the limit infimum of your sigma, okay, which is the analog of lambda here, is at least square root of dr minus 1 plus square root of dc minus 1. And in case you have a balanced Ramanujan, if you have a balanced bigraph, then of course this is it. We end up getting the same bound as from the Allen-Bopana theorem. Okay, so just as we had the notion of Ramanujan graphs, now in a very similar way, we can define the notion of Ramanujan bigraphs. So a dr-dc biregular bipartite graph is said to be a Ramanujan bigraph if sigma is at most square root of dr minus 1 plus square root of dc minus 1. Note the following. Given a d-regular graph, we know that d is its largest eigenvalue. So a Ramanujan graph, by definition, is one for which the lambda, the ratio of lambda over lambda sub 1 is as small as possible, okay, in view of the Allen-Bopana bound. Similarly, when you have a dr-dc regular bipartite graph, A Ramanujan bigraph is one in which the ratio of sigma over sigma sub 1 is as small as possible. This is in view of the Feingley bound. Now we come to questions about existence of Ramanujan graphs and bigraphs. So the basic question is, how pervasive are these graphs and bigraphs? So there's a very nice theorem of Friedman in 2003 which tells us the following. If you fix D and let your number of vertices n go to infinity, then the fraction of D regular n vertex graph that satisfy the Ramanujan property, it just keeps increasing and it comes closer and closer to 1. Similarly, in the setting of Ramanujan bigraphs, you have an analogous theorem proved by Brito, Dumitrio, and Harris in 2018. Here you fix dr and dc, and you let nr and nc go to infinity, subject, of course, to the bipartite condition. Then, with this condition, the fraction of dr dc biregular graphs, which are Ramanujan, this fraction approaches 1. So this means that what these theorems tell us is that Ramanujan graphs and bigraphs are very pervasive. They are spread in nature around us. But despite their prevalence, an interesting aspect, an intriguing aspect of these graphs is that there are relatively few explicit methods for constructing Ramanujan graphs and bigraphs. It is this, here we should also recall one of the most celebrated theorems in recent times by Marcus, Spielman, and Srivastava in 2015, which says that for any D greater than 2, there exist infinite families of D regular bipartite Ramanujan graphs. So this again brings us back to the question of specific examples of Ramanujan graphs and bigraphs, and not just one or two examples. We'd like to construct large families of these graphs or bigraphs. So here are some questions. Given D greater than or equal to 3, can we construct explicitly a sequence of integers n sub I with n sub I going to infinity and a corresponding set of D regular Ramanujan graphs with ni vertices? Similarly, given fixed degrees dr dc, can we construct explicitly a sequence of integer pairs nr nc and a corresponding set of Ramanujan bigraphs with nr nc vertices? Now, in the previous two questions, we were fixing the degree. Now we ask a slightly different question. Is it possible to permit D itself, or drdc more generally, itself to increase to infinity in the case of Ramanujan graphs or Ramanujan bigraphs as nr and nc keep increasing? So now in the context of Ramanujan graphs, there are some explicit constructions, and these constructions are very closely related to extremely important theorems in number theory and representation theory. So one of the earliest constructions of Ramanujan graphs is the famous construction of Lubotsky, Phillips, and Sarnak in 1988. So they constructed an explicit family of D regular n vertex Ramanujan graphs where D is equal to p plus 1 and n is equal to q times q square minus 1, where here p and q are both prime numbers congruent to 1 mod 4. I'll make some more comments about this construction shortly, but notice here what we can have is we can actually fix a prime p congruent to 1 mod 4. So we have a fixed D, and we can have a sequence of primes q which are congruent to 1 mod 4 going towards infinity. And so this way we have an explicit family of Ramanujan graphs with increasing size of vertices. At the same time, Margulis also had an explicit construction of an infinite family of Ramanujan graphs with exactly the same parameters as above. And in 1992, Winnie Li described graphs that would conform to the third question that we just asked. So here you've got Ramanujan graphs of degree d equal to q plus 1, and the vertex size is either q square plus q plus 1, or certain other expressions involving q cube. Okay, so here q is a prime power in general. Okay, so here as the size of the vertex set increases, so does the degree of these graphs. Then there's another example by Morgenstern in 1994, where he constructed an infinite family of d-regular Ramanujan graphs with d equal to p to the a plus 1 for any prime p and any a greater than or equal to 1. Now, there are some other constructions of Ramanujan graphs as well, but the reason I have written these, I'm just going to discuss these four, is that essentially they can be interpreted as Cayley graphs. So what is this technique of constructing Ramanujan graphs? Let us take G to be a finite abelian group. Actually, we don't necessarily need abelian groups. We could take G to be an abelian group. And we let S denote a symmetric subset of G with D elements. So by symmetric subset, we mean that X is in S if and only if the inverse of X is also in S. So we now construct the graph as follows. The elements of G are the vertices of this graph, and two vertices X and Y are connected by an edge if XY inverse lies in the set S. And in this way, it turns out that capital X is a d-regular graph, d being the cardinality of the symmetric set S. And if we take a character of the group G, we denote the following character summation of, we take all the elements S running over the symmetric set S, and we sum up the character values chi of S over these elements. We denote this as lambda sub chi. So it turns out that all eigenvalues of your graph X are given by these character sums. In particular, if you take the trivial character chi sub 0, you get the trivial eigenvalue D. And this tells us that if you have a situation in which, other than the trivial character, the absolute value of these character sums, lambda sub chi, are bounded above by 2 times square root of d minus 1, then X will turn out to be a d-regular Ramanujan graph. So the examples that I just mentioned are examples of Cayley graphs. So in particular, if you take the construction of Lubotsky, Phillips, and Sarnak, these can be interpreted as p plus 1 regular Cayley graphs, where the underlying group is either PSL2 Z mod QZ or PGL2 Z mod QZ, depending on certain properties of the primes with respect to Q. And in order to show that these graphs satisfy the Ramanujan property, we have to use character sum estimates coming from the Ramanujan Deligne bound from the theory of modular forms. So this is a reason why the Ramanujan graphs are actually named after Ramanujan. Okay, now some thoughts about Winnie Li's construction. So suppose we have a finite field, okay, f sub q, where q is some prime power. And let us take f sub q square to be a degree 2 extension of f sub q. Here the generating set S is said to be the set of all primitive, is taken to be the set of all primitive elements of f sub q square, that is the set of all elements of multiplicative norm 1. Now S is symmetric and it contains q plus 1 elements. And again, by a result of Deligne, for every non-trivial character chi sub I on the additive group of f sub q square, the absolute value of the corresponding character sum is bounded above by 2 times square root of q. And therefore, we have a construction of another example of a Ramanujan graph. So the Cayley graph with f sub q square as the group and S as the generator set has the Ramanujan property, thanks to Deleuze's estimate. But the main difficulty in executing this construction is that as yet there is no polynomial time algorithm to find all elements of the set S. So in 1996, Professor Spalensky obtained for Q equal to P to the R an algorithm which will return a primitive element in the underlying field in time O of P raised to the R over 4 plus epsilon. Okay, and this still remains the best known, the most efficient algorithm to return a primitive element of the field F sub Q. However, it is not polynomial time, and currently there are no polynomial time algorithms for implementing the Winnie Li construction. So this is a genuine problem in actually executing this construction. Okay, another very important observation about limitations of the Cayley graphs method is the following. There's a theorem of Friedman, Multi, and Tillich in 2003 says the following. If we have a Cayley graph X with respect to an abelian group G, then absolute of lambda of X is greater than or equal to D minus O of D over N raised to the 4 by D. So if you have a fixed D and you let N go to infinity, then for sufficiently large N, this theorem tells us that the Cayley graph, you see, absolute of lambda of X is coming closer and closer to D. So therefore, the Cayley graph is not a Ramanujan graph. And so if we want to construct Ramanujan graphs for a fixed degree D and N going to infinity using the method of Cayley graphs, then the underlying groups cannot be abelian. So this is a limitation of the method of Cayley graphs. There are several very other types of methods to generate Ramanujan graphs, and I will talk about them soon. So we can also talk about construction of Ramanujan bigraphs. So this is of particular interest in the talk. So here, again, some theoretical work has been done. In particular, Christina Ballantyne and Sio Boteru in 2011 have a paper in which they construct a roadmap for constructing Ramanujan bigraphs. And subsequently, Ballantyne with Fagan, Ganapati, Kuhl, Morishat, and Wooding in 2015 came up with some abstract constructions of Ramanujan bigraphs and these are unbalanced Ramanujan bigraphs with degrees p plus 1, comma p cube plus 1. Okay, here p runs over various primes p, which are, for example, they are congruent to 5 mod 12, or they could be congruent to 11 mod 12. So on a related note, Evra and Parzanchevsky in 2018 also have some abstract constructions of infinite families of Ramanujan bigraphs with degrees p plus 1 and p cube plus 1, but here their primes are congruent to 3 mod 4. For each suitable choice of p, the work of these authors leads to an infinite family of Ramanujan bigraphs. However, at present, these constructions are not explicit in terms of resulting in a biadjacency matrix of zeros and ones. The authors have, we interacted with some of the authors, and we have been informed that they are working, trying to make these abstract constructions explicit is currently work in progress. Okay, so let me also recall here again another result of Marcus, Spielman, and Srivastava, which says that given any C comma D, we have an infinite family of Ramanujan C comma D bigraphs. Okay. So this brings us to the main content of the work that I'm going to report on today. So this is recent joint work with Shantanu Prasad Bernwal and Professor M. Vidyasagar. It is to appear in the Ramanujan Journal, and all the results that I'm going to talk about today form a part of Shantanu's PhD thesis. So to begin with, here are certain families of Ramanujan bigraphs for which we have very explicit constructions. And by explicit, we mean we can actually immediately construct we know exactly what the biadjacency matrix looks like. So the parameters here are LQ times LQ comma Q square, where Q is a prime power and L is a positive integer between 2 and Q. Not prime power, prime number. That's extremely important. I'll let you know why. On a related note, we also have Q square comma LQ bigraphs, where again Q is a prime and L is any integer greater than Q. In particular, if we take in the first instance, if we take L equal to Q, we are able to generate a new class of Ramanujan graphs, which does not match any of the known examples of Ramanujan graphs. And there is one contrast here in comparison with the previous constructions of Ballantine et al. That I talked about. Given a pair of integers L comma Q, we can construct only one Ramanujan bigraph. Okay, so let's just go over the method of construction of these unbalanced Ramanujan bigraphs. The method is really simple, very elementary, and it gives us an explicit biadjacency matrix immediately. In fact, the graphs are constructed by assigning something which turns out to be a valid biadjacency matrix. So here's what we do. We take a prime number Q and we let P to be a Q by Q square matrix. In fact, let P denote the cyclic shift permutation matrix. So what are the entries of P? If J is congruent to I minus 1 mod Q, then P sub ij is equal to 1, and it is 0 otherwise. So the matrix P is simply a shift of the identity matrix. You can take the identity matrix, shift the first row to the bottom of the matrix, and then raise the other rows by one row above. So that is basically the matrix that we are talking about. And we note immediately that the transpose of the cyclic shift matrix is exactly equal to its inverse. Another important fact is that if you take this matrix P and raise it to the power Q, you end up getting identity. So if K is congruent to L mod Q, then P to the K is equal to P to the L. Okay, now here is a nice fact which uses the primality of Q. So suppose we have all possible residues modulo Q, and K is a non-zero integer with absolute K less than Q. So it is, in other words, it is a non-zero residue class mod Q. Then as S runs over all the residue classes mod Q, so does K times S. And therefore, because of the previous equality, we immediately see that if we take P raised to the Ks and sum from S going from 0 to Q minus 1, this turns out to be equal to sum of P to the S as S runs from 0 to Q minus 1. And this turns out to be equal to that Q by Q matrix in which all entries are exactly equal to 1. Okay. Now what we do is we define the array code, what's called the array code Q square by LQ matrix. It comes from the theory of error correcting codes. So we have this matrix C of Q comma L, okay, which we define as combinations of blocks coming from P and its various powers. So it's sort of reminiscent of the Vandermonde matrix. So what we now do is, so this turns out to be the way we've defined it. This is a Q square by LQ matrix. And we can define the biadjacency matrix of a biregular graph, call it B, and this B is equal to C transpose if L lies between 2 and Q. And on the other hand, if we are taking L to be something greater than Q, then we just take the matrix C. With this in place, the first theorem is that, so we take L to lie between 2 and Q. So that's the first case. And let B, as we constructed previously, so in this case it is C transpose, let it represent the biadjacency matrix of an LQ comma Q square biregular graph. It turns out, it can be shown by some work, that it has a simple singular value of root QL, that is known, and all the singular values other than root QL are just root Q with a multiplicity of L times Q minus 1 and 0 with the multiplicity of L minus 1. And therefore, B represents the biadjacency matrix of a Ramanujan bigraph. Okay, so a brief idea of proof. So what we have to do is we have to find out what are the singular values of B. So we take the matrix B transpose B, which is by the definition of the way we defined it is just C times C transpose of the matrix C. And we use a block partition to sort of divide this matrix into more appropriate blocks of smaller sizes. And it turns out that if you take any I and j lying between 0 and L minus 1, remember here L was less than or equal to Q, so L minus 1 is strictly less than Q. If you take the ijth, so C times C transpose sub I comma j is that matrix block which can be composed with the help of the following formula. So you have to take the ith row block of P and the jth column block of P transpose. And very nicely, very conveniently, using the fact that P transpose is P inverse, this just turns out to be P raised to the I minus j times S, where S runs over 0 and 0 to Q minus 1, all the residue classes mod Q. Now I minus j, since I and j lies between 0 and L minus 1, absolute of I minus j is strictly less than Q. And if in particular, if I is not equal to j, then from the fact that Q is a prime, we end up getting that the sum of P raised to the I minus j times S, as S varies from 0 to Q minus 1, just turns out to be that Q by Q matrix, all of whose entries are exactly equal to 1. And when I is equal to j, this matrix just turns out to be Q times the identity over Q, identity square matrix. So then with some more work, so this is the crucial place where we use the fact that Q is prime, and with some more analysis, we are able to derive all the singular values that I mentioned in the theorem. Okay. The other theorem relates to when L is greater than Q. So here we don't have the analysis here is not as comfortable as in the previous case, because your L is greater than Q. Here, since your L was strictly less than Q, you had this matrix sum identity. So here we have to divide the study into two smaller cases, either when L is 0 mod Q or when L is not equal to 0 mod Q. So there are different singular values that show up in these cases. However, all of them end up satisfying the Ramanujan condition. So this is also another example, a very explicit example of an unbalanced Ramanujan bigraph. Okay. And as I mentioned before, when we take L to be equal to Q, the previous theorem leads to the following corollary. We end up getting the biadjacency matrix of a Q square comma Q square bipartite balanced Ramanujan graph with degree Q. Okay. So here in this case, your eigenvalues turn out to be q and square root of q with a multiplicity of q times q minus 1. And the remaining q minus 1 eigenvalues are 0. Okay. So now there's another aspect in the few minutes that remain that I'd like to comment on another aspect of our work, namely that if we have a Ramanujan bigraph, can we perturb the edges of the bigraph in such a way that after perturbation, you still retain the Ramanujan property of the perturbed bigraph? So this is a good time to understand the motivation behind these explicit constructions. So this work was carried out by Bernwal and Vidyasagar. So it relates to the matrix completion problem in engineering. So suppose you have a matrix, okay, of size nr by nc, which is unknown other than a known upper bound R on the rank of the matrix. And let us say we have a small subset of the entries for which we know what the values are. So we call this a sample set. And suppose we can measure entries in the sample set using what we know about the sample set as well as the bound on the rank of a matrix. Is it possible to determine the unknown matrix X completely and exactly? This is the matrix completion problem. And Bernwal and Vidyasagar have pursued this line of inquiry using Ramanujan graphs, and they have shown that if the sample set omega is chosen in a deterministic way as the edge set of a Ramanujan bigraph, then the answer to this question is in fact yes. Okay. Now this leads to another question. In the kind of applications that they are interested in, the sample set that we know needs to be disjoint from a certain set M, which we call the prohibited edges. So let me explain this clearly now. Suppose we are given vertex sets VR and VC, where the cardinality of VR need not necessarily equal the cardinality of VC. And as before, I'm just repeating notation from before, these have cardinalities NR and NC. We are also given the degrees DR, DC. Moreover, we are given a set M contained in VR cross VC, which is called the set of prohibited edges. So our objective is to construct a DRDC bipartite Ramanujan graph such that the edge set of this bipartite Ramanujan graph is disjoint from the set of prohibited edges that we have chosen, the prohibited set M. And from the point of view of applications, we don't need M to be very big. M usually has small cardinality. So we'll make this more explicit shortly. So let's continue discussing perturbing a Ramanujan bigraph. So as before, we consider a DRDC biregular Ramanujan bigraph with a given biadjacency matrix. And let omega be its edge set, whereas let M be the set of S many prohibited edges. So what we are asking is if we can perturb the biadjacency matrix E in such a manner that the corresponding graph does not have any edges from the set M, which you have already fixed, and it is still a DRDC biregular Ramanujan bigraph. So even after perturbations, not only does it manage to save the bipartite property, but also the Ramanujan property. So in this connection, we also have the following theorem. Suppose E is the biadjacency matrix of a DRDC biregular Ramanujan graph. Let us define mu of dr comma dc as this optimal value of the non-trivial singular values So square root of dr minus 1 plus square root of dc minus 1 coming from the Feng-Li bounds. So let sigma 2 denote the second largest singular value of E. So in a Ramanujan bigraph, we know that sigma 2 has to be bounded above by mu of dr comma dc. What we are interested in is the difference between this expected bound and the actual second largest singular value. So suppose we have an integer p, positive integer p, such that 2 times p is at most mu minus the second largest singular value. And suppose we have the following restrictions on the set M, namely M does not contain more than p values of j. So for any fixed I in the vertex set VR, there are at most j many elements, vertices in n sub c, so that ij lies in the set of prohibited edges. And the same thing happens in the reverse direction for every fixed j in the vertex set v sub c. So if this p, so suppose we have such a p for this happens, and in addition, 2 times p is less than or equal to mu minus the second largest singular value, then we can construct a DRDC biregular Ramanujan graph whose edge set is disjoint from the set of prohibited edges M. So what we can do is actually, when I don't have time to go over the proof, but briefly speaking, we start with a bipartite, we start with the Ramanujan bigraph, and then we perform some procedures to eliminate prohibited edges from them. So now before I conclude, some comments about the spectra of Ramanujan bigraphs. So you may have observed that the previous theorem shows that if the gap between the second largest singular value and the bound mu increases, then more perturbation is possible in your Ramanujan graph. However, we also learned the Allen-Bopana bounds and the Feng-Li bounds for bigraphs, which shows that as the graphs keep growing in size, the gap between mu and sigma 2 is in fact going to 0. So here the degrees remain fixed, right? For both these bounds in both the theorems of Allen-Bopana and Feng-Li, the degrees were fixed. Therefore, this does not pose a limitation to our scenario, because in the constructions that we presented, the degree of the bigraph increases along with the size of the graph. So your mu minus sigma 2 also keeps growing along with the degrees dr comma dc. Concluding remarks. So as I mentioned before, there are relatively few explicit constructions of Ramanujan graphs and balanced as well as unbalanced bigraphs. Here we presented explicit constructions of an infinite family of unbalanced Ramanujan bigraphs, and this we believe is the first such explicit construction of a family of unbalanced Ramanujan bigraphs. So these explicit constructions are available for only certain combinations of degree and size, but it makes for a very good beginning. And it is known from the work of Marcus Spielman and Srivastava that Ramanujan graphs and bigraphs are known to exist for all degrees and all sizes. And therefore, this opens up it opens up an interesting field of inquiry about constructing unbalanced Ramanujan bigraphs for a variety of degrees and sizes. And Bernmal and Vidyasagar show that it is there's a very nice and useful application of Ramanujan bigraphs in engineering, and they show that it is in fact possible to guarantee the exact completion of an unknown matrix, provided the sample set that you already knew corresponds to the edge set of a Ramanujan bigraph. So I think I'll stop at this stage. Thank you.
Thank you, Kaneenika, for the beautiful talk. Anybody has any question or comments? Please go ahead. So just unmute yourself and ask. Sorry, so there is no restriction on L, right? L can be any number, right? Q has to be prime.
Q has to be prime.
And L bigger than Q is where it is a little bit more painful, a little bit.
Yeah, we have to be a little careful of whether it is 0 mod Q or not 0 mod.
For L less than Q, you could break it into parts which are of at least length L, and because Q is prime, that helped you figure out this part. Whereas the other way is complicated because L is bigger than Q, so you have to read it mod Q, right?
Yes.
Sure. Okay, if there is no more question, let's thank Kaneenika once again.
Thank you.